This lecture discusses divide and conquer algorithms. Particularly, we analyze and discuss the time complexity of divide and conquer algorithms. Here's the roadmap of what we will cover. In this lecture, we will start by providing a general definition of divide and conquer algorithms. After that, we will dive into an algorithm example, the binary search. We will go over the algorithm and conduct a time complexity analysis on it. As we do that, we will introduce a general approach to analyze time complexity of divide and conquer algorithms, the recurrence tree method. So what's divide and conquer? You may have heard of the term for many times, but don't know its accurate definition yet. Divide and conquer is not a specific algorithm. Instead, it's a general algorithm design paradigm. An algorithm is like a specific recipe for solving a problem. An algorithm design paradigm is like a general cooking style or method, such as grilling, baking, or steaming. It provides a framework or philosophy for creating recipes. For example, divide and conquer is a cooking style that involves breaking the task into smaller pieces, like cutting ingredients into portions, and solving each part independently before combining them. Binary search, as an algorithm, is a recipe developed using this cooking style. There are three key steps in divide and conquer algorithms, including divide, conquer, and combine. The divide refers to dividing the problem into subproblems that are similar to the original but smaller in size. Conquer means to solve the subproblem recursively. If a subproblem is smaller enough, then you can solve that directly. Last, combine means to combine the solution to the smaller subproblems to create a solution to the original problem. All divide and conquer algorithms follow this pattern. To help you make sense of it, we will look at an example, the binary search. On the screen, you can see the pseudocode of binary search. What problem does it solve? It searches for a target element from a linear data structure like an array. Putting binary search aside, if your goal is to find a given target element in an array, you can of course traverse the array from the beginning to the end. If your target is found, then your job is done. If not, the target is not in the array. This is what we call linear search. In comparison, binary search is more efficient, but it comes with a big assumption. What's the assumption? The given array is already sorted. With that assumption, at each step, binary search divides the search space, or say the array, into two halves by comparing the target element with the middle element of the current range. Based on the comparison, it eliminates one half of the search space, either the left or the right one. Then, it focuses the search on the remaining half. In case you don't know how it works, let's take a look at the code and make sense of it using an example. The algorithm takes two parameters, the array and the target. Remember, the array is fully sorted. Let's assume it's in an increasing order. So binary search starts by making two indexes. The starting index at 0 and the ending index at array's length -1. The starting index is denoted as, short for start, and the ending index is denoted using E, short for end. While S is smaller than or equal to E, you will calculate and find the middle index. If the element sitting at the middle index is equal to the target, you would return mid, which is the index of the target element. If the element is smaller than the target, you would update the starting index to the middle index +1. By doing that, you basically eliminate the first half of the array, starting from S to the middle index. The reason is that if the element in the middle is even smaller than the target, everything comes before it, on its left, will also be smaller. So there's no point to compare them to the target anymore. By updating S to mid +1, you will continue this while loop, but you won't look at the first half of the array anymore. On the other hand, if the element is bigger than the target, it would update the ending index e to the middle index minus 1. By doing that, you will eliminate the second half of the array, starting from the middle index to the original ending index in the future iterations of the while loop. The rationale is similar. The array is sorted. If the element in the middle is even bigger than the target, anything that comes after it, on its right side, will also be bigger. So you should save your energy by searching in the section where elements are smaller, which is the left half of the array. Okay? So when the while loop terminates, yet the target is still not found, it would return -1, indicating that the target is not found. Let's go through an example to help you make sense of the binary search. On the right side of the screen, you can see a sorted array in increasing order. In case the two rows confuse you, the first row represents the values in the array, and the second row represents indexes of the array. The target to search for, in this case, is 2. So the starting index s and ending index e are initialized to 0 and 7 respectively. The middle index is calculated to 3. The corresponding element of the middle index is 5. 5 is bigger than the target. The array is sorted, so all the elements coming after 5, they would also be bigger than the target. There's no need to compare them to the target anymore. As a result, we will go to this line and update e to mid -1, which is index 1, whose corresponding value is 2. 2 is equal to the target, so we will return the index of 1. Then your job is done here. You see, it's much faster than traversing the whole array and comparing each element to the target. You essentially cut the array by half in each iteration of the while loop. Let's look at another example to make sure that we are on the same page. This time, the input array stays the same, but the target becomes 9. The starting index is 0, the ending index is 7, so the middle index is 3. And corresponding to an element, that's 5. 5 is smaller than 9, so this line will be triggered. It will update s to mid +1, which is index 4. Because s is still smaller than e, so the next iteration of the while loop will be triggered. The mid is recalculated to 5 this time. The element corresponding to index 5 is 7. 7 is still smaller than the target 9, so this line will be triggered again. It will update s to mid +1, which becomes 6. Because s is still smaller than e, so the next iteration of the while loop will be triggered. In the next iteration of the while loop, the middle index is recalculated and updated to 6, whose corresponding element is 9. 9 is equal to the target. It will return the index, and the job is done. Now we should be on the same page of how binary search works. You may still wonder how this is divide and conquer. It's hard to see any divide and conquer here. Well, binary search is considered a divide and conquer algorithm. If the iterative implementation hides that from you, we can list the recursive implementation by its side. Both implementations achieve the same thing. The recursive version takes 4 parameters instead of 2, including the sorted array, the target value, the starting index, and the ending index. In this implementation, there's no while loop. If the element at the middle index is equal to the target, it would return the index. If smaller, it will call binary search again on the second half of the array and return its result. Otherwise, it will call binary search on the first half of the array and return its result accordingly, regardless whether it's iterative or recursive. Binary search divides the search space into half by comparing the target element with the middle element of the current range at each step. That's what is known as the divide step. Based on the comparison, the algorithm eliminates one half of the search space. It's going to either be the left half or the right half. And then the algorithm would focus the search on the remaining half. That's what is known as the conquer step. While binary search doesn't explicitly combine results like some other divide and conquer algorithms, like merge sort, the process of halving the search space and eventually finding the target element aligns with the essence of the divide and conquer algorithm approach. So you know what binary search does and why it's a divide and conquer algorithm. Let's analyze its time complexity. Let's start with something simple. The best and the worst case analysis. The best case is trivial. It happens when the element sitting in the middle of the array is equal to the target. Like this example, where the target is 5, and the element sitting in the middle of the input array is also 5. In this case, this line will be triggered, and the middle index will be returned. The while loop will be terminated in one iteration. That said, binary search only takes a constant number of steps, or say constant time in the best case. What about the worst case scenario? The worst case means that the while loop runs for as many iterations as possible until the starting index is bigger than the ending index. In other words, the search space will be halved and halved for many times until it becomes empty. For example, when the target is 11 for the same input array, it will have a worst case. It will keep halving the search space for 4 times, starting with the whole array. Then to this, then to this, then to this. After that, S will become bigger than E, ending the whole while loop, and -1 will be returned. At the start, you have a sorted array of size n, which is the input array length. In our case, that's 8. In each step, binary search eliminates half of the elements in the search space by comparing the target with the middle element. If the target is smaller, it eliminates the right half. If the target is bigger, it eliminates the left half. In our case, the target is always bigger, so the left half always gets eliminated. After the first step, the search space is reduced to n divided by 2, which is 4 in our case. After the second step, it's further reduced to n divided by 4, which is 2 in our case. After the third step, it's n divided by 8, which is 1 in our case. This process essentially continues until the search space becomes 1 element or less, at which point the target is determined to be absent. So at each step, the search space size is divided by 2. This can be expressed mathematically as, after k steps, the size of the search space is n divided by 2 power 2k. Remember, n represents the input size, the size of the sorted array, where k represents the number of the steps. Each step represents an iteration of the while loop. So the process stops when the search space becomes 1. Okay? Rearranging this, you will have 2 power 2k is equal to n. Taking the logarithm base of 2 on both sides, you will end up with k is equal to log of n. Thus, binary search requires about log n steps to complete. Since there are log n steps in the worst case, the total time complexity is big O of log n. This conclusion is based on some intuition and some leap of faith. It's not based on a generalized method. We will get to the generalized method later. Before that, it's worth mentioning that many divide and conquer algorithms have a logarithmic component in their time complexity, especially when the divide step involves splitting something in half. Now you know that the time complexity of binary search based on our intuition. Let's get a more generalized method for analyzing its time complexity and the time complexity of all divide and conquer algorithms. Before we do that, we need to introduce a new concept called recurrence relation. So, a recurrence relation is a mathematical equation that defines a sequence of values based on its previous terms. It describes how the time complexity of a problem is related to two things: the size of the input and the complexity of smaller subproblems created during the algorithm's execution. It's commonly used to model and express the time complexity of divide and conquer algorithms, such as binary search. When you have a recurrence relation, it makes solving the time complexity of divide and conquer algorithms much easier. By solving a recurrence relation, we can determine the time complexity of its corresponding algorithm. In other words, it is still a time complexity function Tn, where n represents the input size, but it describes the relationship between Tn at this step and Tn at the next step as the recursion is triggered. An example is provided to help you make sense of it. So what sits on the left side of the equation describes the total time complexity of this function Tn. The corresponding divide and conquer algorithm does some work at the current step, which takes a constant number of steps. In this example, that number of steps is 1. As recursion happens, the same function is executed on half of the input size. That's how you get T of n divided by 2, because the only thing changed here is the input size. This equation describes the time complexity of the current step and the next step. By step, I mean the triggering of the recursive call. This may still sound fuzzy. That's why we need to look at a more concrete example. Let's go back to the binary search. We know that binary search can be implemented iteratively and recursively. They achieve the same effect. To make it easier to understand how binary search works, we used the iterative version. Now, to make it easier for you to understand how we derive the recurrence relation of binary search, we will use its recursive implementation. Our goal is simple. We want to extract a recurrence relation for binary search. In other words, we want to describe the relationship between the time complexity at the current step and the next step. To scaffold your thinking, I have listed this expression here. As long as you can figure out what lines are executed at the current step and what time complexity of those lines have, you will be halfway through the task. So what lines are executed under binary search at the current step? These lines would be executed. Okay? That takes constant number of steps, right? Remember, we are talking about the worst case, so you can forget about the if condition. Either else if or else will be triggered. Both else if and else returns the recursive call of binary search. However, the arguments are different. By replacing s with mid plus 1 or by replacing e with mid minus 1. You're eliminating the search space, or say the input size, by half. As a result, the recurrence relation can be expressed as T of n is equal to T of n divided by 2 plus theta of c. T of n divided by 2 represents the time it takes to trigger either of the two recursive calls on the halved input size. Theta of c represents the constant number of steps it takes to run these lines. This is the recurrence relation of binary search. It describes the time complexity at the current step in relation to the time complexity of the next step. As you can see, the time complexity function t shows up at both sides. So this doesn't tell us how efficient binary search is. To answer that, we need the help from the recurrence tree method. This is the generalized method to solve time complexity of divide and conquer algorithms we have mentioned. It involves at least 4 steps, including get the recurrence relation, draw the recurrence tree, calculate the work at each step, or say at each level, and sum the total work. Let's use binary search as an example to make sense of this method. We already have a recurrence relation, so we are done with step 1. Step 2 is about drawing the recurrence tree. Think about that we are executing binary search on a set of arguments, including the array, the sorted array, the target, the starting and ending indexes. So the array is the example we studied, and the target is 11. The starting index is 0 and ending index is 7. A series of recursive calls will be triggered when the binary search is executed with this set of arguments, like this. In every recursive call, the starting and ending indexes determine the search space, or say the problem size. As you can see, the problem size is reduced by half every time when the next recursive call is triggered. Based on such understanding, we can draw a tree-like structure to facilitate our investigation of the time it takes to execute a binary search on a generalized problem size of n. We will use 2 columns. The left column indicates the problem size, or say the subproblem size, as recursion is triggered. The right column indicates the time it takes to address the work at a step corresponding to the subproblem size in the same row. Of course, the time it takes to do the work on the corresponding step is outside of recursion, because the time of the recursive call will be accounted for in the next step. Why is this method named the recurrence tree method? Because as you list the subproblem size of recursions triggered at each step row by row, you will have a better idea of the number of recursive calls being triggered, which is helpful for you to sum up the time it takes at each step so that you can deduce the total time it takes to execute a binary search tree algorithm. So what is the initial problem size when the binary search is executed, assuming that the initial input is an array of size n? The problem size is of course n. The time it takes to do the work outside of the recursion at this step is simply these 3 lines. They take constant time to be executed, so we will list C in the same row corresponding to this problem size, where C is a constant number. The execution of this binary search on a problem size of n will trigger another binary search on a halved problem size in either of the 2 recursive calls. The subproblem size is n divided by 2. However, the time it takes to do the work at this step remains these 3 lines, which takes a constant time to run. So we will list them side by side. Subproblem size is n divided by 2, and the time outside of recursion corresponding to this problem size remains c. This recursion will trigger another recursion on a further halved problem size. Yet, the time it takes to do the work outside of the recursion at next step remains the same. So we can list them side by side, the problem size as n divided by 4, and the time remains c. This process will continue at each step. It will reduce the problem size by half, like this, until it becomes 1. However, the time it takes to do the work outside of the recursion remains the same as a constant number. Now you have a tree structure fully drawn. Based on this structure, you have enough to calculate the time complexity function by adding up all the time in the right column together, because they are the actual time it takes to get things done in every recursive call that's being triggered along the way until the problem size becomes 1. To get the time complexity function, you need to figure out how many C there are. In other words, you need to know how many recursions are triggered, or say how many steps it takes to reduce n until it becomes 1. This becomes a question that we studied if you focus your attention on the left column. How many times can you keep dividing n by 2 until it becomes 1? The equation remains the same. It takes k steps to achieve this. The relationship between n and k will be n equal to 2 power 2k. If you apply the logarithmic to both sides, you will have log n that's equal to k. That said, it takes log n steps to keep dividing n by 2 until it becomes 1. That said, there are log n of c. You can add them up to derive the time complexity function as Tn equal to c multiplied by log n. C as a constant number won't matter when you try to determine the upper bound, so the upper bound of Tn will be just the log n, expressed as Tn belongs to big O of log n. In summary, the recurrence tree method requires you to figure out the relationship between subproblem size of recursion at this and the next step, as well as the time it takes to address the work outside of recursion corresponding to a problem size. You will start with a generalized problem size n and develop a tree-like structure by filling out these two columns row by row, where each represents a problem size and its corresponding time to do the work outside of recursion. In the end, you need to add up all the time, or say combine all the time it takes to calculate the time complexity function. In this video, we covered the definition of divide and conquer algorithm and discussed the recurrence relation and the recurrence tree method that is used to deduce the time complexity of divide and conquer algorithm. We achieved this by covering the binary search algorithm. In the next video, we will cover a different divide and conquer algorithm, the merge sort. We will revisit recurrence tree method and cover a different approach to time complexity analysis on divide and conquer algorithm, which is the master theorem.